Okay, so today we have our last lecture of this course, and the lecture will be devoted to compact operators. So we start with a definition of compact operator. So suppose we have two Banach spaces, X and Y. Again, we return to our initial convention that the base field is either the field of real numbers or the field of complex numbers, and we denote it by bold K. And we give the following definition. We say that a linear operator T from X to Y is compact if the image of the unit ball of X is relatively compact in Y. Which means that the closure of the set is compact in Y. And since Y is a Banach space, so it is complete, we see that relatively compact is equivalent to totally bounded. This equivalence was discussed at the previous lecture. Well, a few words about the history of this notion. The notion of compact operators, of a compact operator, goes back to works of Hilbert and Schmidt of the beginning of the 20th century. They considered a special case where both X and Y are L2 spaces. That is, either little L2 spaces or big L2 spaces. And also, they didn't consider linear operators at all. Instead of working with linear operators, they considered bilinear forms. Well, actually, it turns out that over the real numbers, the language of bilinear forms is more or less equivalent to the language of linear operators. The first man who gave the definition of a compact operator and who actually understood the importance of linear operators in functional analysis was Friedrich Ries in 1913. First, he also considered only the case of Hilbert spaces, or more exactly of L2 spaces, and his original definition was different from the above one, and it involved the notion of weak convergence. The modern definition of a compact operator is also due to Ries. In 1918, he published a paper which was very important, and actually it was one of the most significant and influential papers in the history of functional analysis. The paper was entitled Linear Functional Equations. And by the way, you can easily find a Russian translation of this paper at MathNet site. So Ries, actually, again, he worked with a special case where both X and Y are spaces of continuous functions on a closed interval of the real line. So he didn't consider general Banach spaces, and this is very natural, actually, because this was 4 years before the general notion of a Banach space was introduced. But amazingly, almost all the results and the methods developed by Ries work in the context of arbitrary Banach spaces. Okay, let's now make some simple observations related to this definition. First of all, let's observe that linear operator T is compact if and only if the image of each bounded set is relatively compact. It's relatively compact in Y for each bounded set B in X. This is almost immediate from the definition because each bounded set is contained in a suitable bowl. Second, let's observe that each compact operator is obviously bounded. Well, indeed, a bounded operator takes, by definition, an operator is bounded if it takes the unit bowl to a bounded set. And here we have a stronger condition. So T is compact if the set is relatively compact. Of course, each relatively compact set is bounded. So every compact operator is bounded. There is a special situation in which the converse is also true. Namely, if T is a bounded operator from X to Y, and the image of T is finite dimensional, and in this case, we say that T is a finite rank operator, then T is compact. Well, indeed, the image is finite dimensional, and we know that each bounded subset of finite dimensional space is relatively compact. So if T is a bounded finite rank operator, then it is compact. In the general case, a bounded operator is not necessarily compact. And the simplest counterexample is the identity map of an infinite dimensional Banach space. So the identity map is compact, even only if X is finite dimensional. And this is immediate from the fact that the unit bowl of an infinite dimensional space is not compact. By the way, let me also say that of course we could also consider a more general situation in which X and Y are Norrand spaces, not necessarily complete. But in this case, we have two inequivalent options. We may say that T is compact if it takes the unit bowl to a relatively compact set or to a totally bounded set. But if we don't assume that Y is complete, then these two definitions are not equivalent. So relatively compact and totally bounded are equivalent for subsets of a complete space. Well, this is not very convenient, of course. And probably this is the main reason why compact operators are traditionally considered only in the context of Banach spaces. Okay, let's introduce some notation. The set of all compact operators from X to Y will be denoted by K of XY. And if Y equals X, then we just write K of X. Well, let's now prove some general properties of compact operators. We have the following proposition. First of all, I claim that K of XY is not just a set. It's a closed vector subspace. K of XY is closed vector subspace of B of XY, or the space of all bounded operators. Second, if we have two bounded operators, T from X to Y, and S from Y to Z, and one of them is compact. So we assume that either SRT is compact, then so is the composition ST. And property 3, which is due to Schauder, you will have a bounded operator from X to Y, an operator T, and T is compact if and only if the dual operator T star is compact. Well, I'd like to say once again that most significant results, most fundamental results of about compact operators were obtained already by Riess in 1918. And this is an exception. So Schauder's theorem was proved only in 1930. Again, this is not surprising because the duality theory wasn't available in 1918 when Riess introduced compact operators. Okay, so let's now prove this result. Part 1. So why is it a vector subspace? Well, we take two compact operators, S and T, and we want to show that their sum is compact. So we apply the sum S plus T to the unit ball of X. And let's observe that this is contained in the sum S of B plus T of B. So for convenience, we'll take the closures here. And these two sets are compact. But it's immediate that the sum of two compact subsets of an ordered space is compact. So as a result, S plus T of B1 is relatively compact. Well, indeed, the product of two compact spaces is compact. And this set is just the result of applying the plus operation to their product. And the plus operation is continuous. So the continuous image of a compact space is compact. Okay, so we see that the sum S plus B is compact. And similarly, we can show that if we multiply S by a number, then we get a compact operator. So the space of compact operators is a vector subspace in B of xy. Now let's show that it is closed. So we take a bounded operator T from X to Y, which is in the closure of K of xy. And we want to show that T is compact. Well, since T is in the closure, for each positive epsilon, we can find a compact operator S. Compact operator S from X to Y, such that the distance between S and T is less than epsilon. Now S is compact. So the image of the unit ball under S is totally bounded. And we can easily find a finite epsilon net. So let F in Y be a finite epsilon net for the image of the unit ball under S. Well, then the triangle inequality readily implies that the same set F will be a true epsilon net for the image of the ball under T.
Excuse me, I've got a bit lost. Do you prove the second part of the proposition now?
Yet, no. At the moment, we are trying to prove that K of xy is a closed vector subspace. So we have already proved that it is a vector subspace. That the linear combination of two compact operators is compact. And now we are trying to show that it is closed. So we take an operator which is in the closure of K of xy, and we want to show that it is compact.
I see, thank you.
Okay. Okay, so F is a finite epsilon net for S of B, for the image of the unit ball under S. And the distance between S and T is less than epsilon. And what is the distance between S and T? This is the supremum over the unit ball. Supremum of S of X minus T of X, where X runs over the unit ball. So now the triangle inequality implies that F is 2 epsilon net for T of B. And since epsilon is arbitrary, we conclude that T is compact. Okay, and so we see that the space of compact operators is a closed vector subspace of B of X, Y. Okay, now part 2. We now have 2 bounded operators, S and T, and one of them is compact. Well, first of all, let's suppose that S is compact. And we look at the image of the unit ball under ST. Well, now T is bounded. So this set, the image of the unit ball under T, is bounded. And S is compact, so it takes bounded sets to relatively compact sets. And so this is a relatively compact set. And this implies that ST is compact. And if we now assume that T is compact, and again we look at the same set, S of T of B1, now the image of the unit ball under T is relatively compact because T is compact, and S is a bounded operator, or equivalently S is continuous. And the continuous map takes compact sets to compact sets. So it takes relatively compact sets to relatively compact sets. So this set is relatively compact. And again, we conclude that ST is compact. Okay, so this proves part 2. And let's now prove Schauder's theorem, which states that T is compact even only if the dual operator T star is compact. Well, let's start with the left to right implication. So we assume that T is compact. T is a compact operator from X to Y. And let K denote the closure of the image of the unit ball under T. So this is a compact subset of Y. We want to show that T star is compact. In other words, we want to show that the image of the unit ball in Y star under T star is totally bounded. So the idea here, the idea of the proof, is to identify this set, with a certain subset in C of K, in the space of continuous functions on K, and then to apply the Arcelor-Scolli theorem. So we start with the following a little calculation. So we take 2 elements F and G in the unit ball. And let's look at the distance between T star of F and, well, maybe I'll write it at the next page. So we calculate the distance between T star of F and T star of G. So this is T star of f is just the composition of f and t, and this is the composition of g and t. And by the definition of the operator norm, this is the supremum over the unit ball f of t of x minus g of t of x. Or equivalent to this is the supremum over the image of the unit ball f of y minus g of y. If we now replace the image of the unit ball by its closure, that is by k, the supremum will be the same by continuity. And what is this? Well, this is nothing but the norm of f minus g in C of k. Or more exactly, not of f minus g, but of, we must take the restrictions of f and g to k. And we calculate the distance between these two functions in C of k. Okay, so let's now look at this chain of equalities, and let's observe that this chain implies the following.
Could you elaborate what is the C of k norm?
C of k norm is just the supremum, the supremum over k. Well, let me write this down more explicitly. This is the
so this is the k that is the subset, not the set of operators.
No, but k. What is k? K is a subset. Well, let me write down the definition of the supremum norm. So this is the supremum norm in C of k. So what is k? K is a subset of y. Here's the definition of k. This is a compact subset of y. And C of k is the space of all continuous functions.
I see. Thank you.
And so we equip C of k with the canonical supremum norm. And we observe that this expression, this one, is nothing but the distance between f and g in C of k, or more exactly, between their restrictions to k. Okay, and now these equalities imply that we have the following map that's denoted by phi. Oh, before we introduce the map, let's introduce some more notation. So let M denote the set of all restrictions to k of linear functionals from the closed unit ball of y star. And this is a subset in C of k. Let's now introduce the following map, denoted by phi, from M to the image of the unit ball under T star. So phi takes the restriction of f to k, where f is a functional from the unit ball of y star. So it takes this function to T star of f. So what can I say about this map? First of all, I claim that it is well-defined. Potentially, it could happen that two different functions, two different functionals, f and g, have the same restriction to k, and we must show that in this case, the right-hand side will be the same if we replace f by g. But this follows from this chain of equalities. because if we have two linear functionals f and g such that the restrictions to k are the same, then we have 0 here, and therefore we have 0 here. And so their images under T star are the same. And so that shows that our map phi is well defined. And the same chain of equalities shows that phi is an isometry. In fact, it is an isometric bijection. This is an isometric bijection. Between M and the image of the unit ball, T star of B1. So it is surjective by construction, and we have just shown that it is isometric. So it is an isometric bijection. And let's recall that we wanted to prove, our goal is to prove that this space, the image of the unit ball under T star, is totally bounded. Now we see that it's enough to show, that M is totally bounded. So to complete the proof, it suffices to show that M is totally bounded. And this is more convenient because this is more convenient than to work with T star of B, because M is a subset in C of K. And we have a useful criterion, the Arcelor-Scully theorem, which states that a subset of C of K is totally bounded, if and only if it is bounded and equicontinuous. Bounded and equicontinuous. This follows from the Arcelor-Scully theorem. Now this is quite easy. First of all, why is it bounded? Well, if we take a linear functional from the unit ball of y, and we take a point in K, so we want to show that f of y is bounded by a common constant, which doesn't depend on f and y. Well, f is in the unit ball, so this is less than or equal to the norm of y. And y runs over K, and K is a compact set, so it is bounded. So this is less than or equal to C, where C is just the supremum of all of norms of elements in K. And this is finite because K is bounded. And so this implies that M is bounded for the supremum norm. And why is it equicontinuous? Well, we now take two linear functionals from the unit ball. We don't need two functionals. We take a linear functional f from the unit ball, and we take 2 points, x and y in K. And let's look at f of x minus f of y. Well, what is this? F is linear, so this is f of x minus y. And the norm of f is less than or equal to 1, so this is less than or equal to x minus y. So we see that M is not just equicontinuous, it has the stronger property of being, let's call it, uniformly one Lipschitz, in the sense that this estimate holds. So if this distance is less than epsilon, then this is also less than epsilon for each f in our space. So we just look at the definition of an equicontinuous family, and we let delta equal to epsilon. And we see that this condition is satisfied. So M is equicontinuous. And this completes the proof. This completes the proof of the left-right implication. So we see that T star is a compact operator. And to prove the right to left implication, so now we want to show that if T star is compact, then T is compact. Well, this is rather easy. We just look at the bidual. Namely, if T star is compact, then, well, we already know that the dual of a compact operator is compact. So we deduce that T double star is compact. Now let's now recall the relation between T and T double star. So after we identify canonically X and Y with subspaces of their biduals, we know that T is just the restriction of T double star to X. And clearly the restriction of a compact operator to a closed subspace is also compact. And this completes the proof. Okay, let's now look at some corollaries of this result. First of all, corollary 1. If X is a Banach space, then K of X, the set of all compact operators from X to itself, is a closed two-sided ideal. Closed two-sided ideal of B of X. Well, it's a closed vector subspace by property 1 from the previous proposition. And it's an ideal by property 2. It's a two-sided ideal by property 2. So the composition of a compact operator with bounded operator is compact. By the way, sometimes for some concrete Banach spaces, it turns out that this is the only non-trivial proper closed two-sided ideal of B of X. In particular, this is true provided that X is an infinite dimensional separable Hilbert space. But on the other hand, there are some more complicated Banach spaces for which we have more ideals. So the structure of the lattice of two-sided ideals of B of X in the general case is quite interesting and non-trivial. But sometimes this is the only one. Okay, now before we formulate the next corollary, let's introduce some notation. We denote by f of xy the set of all finite rank operators, all bounded finite rank operators from X to Y. Finite rank means that the dimension of the image is finite. Clearly, this is also a vector subspace of V of xy, and if y equals x, then we write just f of x. Now, corollary 2, if we consider the closure of this subspace, the closure of the subspace of finite rank operators, then it is contained in compact operators. So we have this inclusion. In other words, if a bounded operator can be approximated by a finite rank operator for the uniform norm, for the usual operator norm, then it is compact. And this is a very useful condition. It is useful when we want to prove the compactness of a concrete operator. Well, not by the definition, but by using this corollary. Well, let's now look how this works. Here's an illustration of this inclusion. Let's look at the diagonal operator. So let's denote by X the little P space, where P is an arbitrary number between 1 and infinity, possibly infinite, or the little C0 space. So alpha is now a bounded sequence that is an element of L infinity. And we consider the diagonal operator M alpha from X to itself, which is just the pointwise multiplication by alpha. So we know that we already know that this operator is bounded. The norm of this operator is just the supremum norm of alpha. So the natural question is, when is it compact? Well, I claim that M alpha is compact if and only if alpha vanishes at infinity. Well, so I claim that M alpha is compact if and only if alpha vanishes at infinity. Well, why is it so? First of all, let's prove the right to left implication. Suppose that alpha vanishes at infinity. Then, for each positive epsilon, we can find a finite sequence B, beta in C00. So C00 is the space of finite sequences. That is, sequences which are eventually zero. Such that the distance between alpha and beta is less than epsilon. This is because the space of finite sequences is dense in C0. If we now look at the distance between the respective diagonal operators, M alpha and M beta, first of all, this is nothing but the diagonal operator corresponding to alpha minus beta. And we know that the norm of this operator is just the supremum norm of alpha minus beta. And this is less than epsilon. On the other hand, M beta is a finite rank operator. And now corollary 2 implies that M alpha is compact. Okay, and now to prove the left to right implication, let's assume that alpha is not an element of C0. So it doesn't vanish at infinity. And this means that we can always find a subsequence which is bounded away from zero. So there is a positive epsilon, and there is a subsequence. A subsequence alpha and k, such that the following inequality holds. Well, as usual, we denote by En the following element of our space. And now, if we now apply M alpha to En(k) and En(L) for different k and L, and look at the distance between these two elements, so they belong to the image of the unit ball, because, well, En is in the ball, the unit ball of X. Well, they are eigenvectors, so this is alpha nk Enk minus alpha nl Enl. And since k and L are different, we assume that k is not equal to L. This can be estimated as follows. This is bigger than epsilon multiplied by the norm of Enk minus Enl, that is 2 to the power 1 over p. And this is a constant. This is a constant. So we see that the image of the unit ball contains an infinite sequence of elements such that their pairwise distances are bounded away from zero. We know that this means exactly that the image of the unit ball is not totally bounded. And so the operator is not compact. And this completes the proof. So once again, I'd like to stress that this result shows that corollary 2 is a very convenient tool for proving the compactness of an operator. If an operator can be approximated by finite rank operators, then it is compact. In some cases, this inclusion, the inclusion of corollary 2, is actually an equality. For example, this is the case provided that Y is a Hilbert space. So we have the following result. Suppose that X is a Banach space and H is a Hilbert space. Then the following equality holds. That is, each compact operator from X to H can be approximated by finite rank operators. Well, let's now prove this result. So we take a compact operator T from X to H. So the image of the unit ball is totally bounded. And let's find a finite epsilon net. F is a finite epsilon net for the image of the unit ball. Let's take the linear span. Let H0 denote the linear span of F. This is a finite dimensional vector subspace of H. A finite dimensional space is closed in H, and we have the following direct sum decomposition. H0 plus H0 orthogonal. And we let P denote the orthogonal projection. The orthogonal projection of H onto H0, which means that T is a bounded linear operator. T is a linear operator from H to itself, which acts by the following formula. If X is an element of H0 and Y is an element of the orthogonal complement, then X plus Y goes to X. Well, clearly P is a finite rank operator because its image is contained in H0. And the same is true for the composition. So P is a finite rank operator on H, and PT is a finite rank operator from X to H. And what I want to do is to show that PT is close to T. If we show that PT is close to T, then, well, this will imply that T is approximated by finite rank operators.
I don't understand. Isn't H0 an infinite rank subspace?
A finite dimensional. Well, look, F is a finite epsilon net. So F is a finite set.
Ah, okay, thank you.
F is a finite set. And we take the linear span of F. So H0 is finite dimensional.
Oh, here is two different Fs. One is for a net and the other for the space of finite rank operators.
Ah, well, script F and just usual F. Well, script F is the set of all compact operators. And this is, well, let's denote it by some other letter. For example, well, S. N is for net. Okay. H0 and H0 is linear span of N. Is it better?
Yes.
Okay, let's continue. So H0 is a finite dimensional space, so PT is a finite rank operator. And let's calculate the distance between T and PT. First of all, we observe that the norm of P is exactly 1. This follows from the Pythagorean theorem. So the norm of x plus y is bigger than the norm of x if y is not 0. But this is exactly the norm of x if y is 0. So the norm of P is 1. Now, since n is an epsilon net for the image of the unit ball, and for each element x in the unit ball of x, we can always find an element y in our epsilon net n such that tx minus y is less than epsilon. And if we now look at the distance between t of x and pt of x, so we can estimate this as follows: tx minus y plus y minus ptx. So now we modify this as follows. Y sits in M, and P is the identity map on M. Actually, it is the identity map on H0. So we can write this in the following way: P applied to Y minus Tx. But P, the norm of P is 1. The norm of P is 1. So the second summand here is less than or equal to the first one. And the whole sum is less than or equal to 2 multiplied by the first summand. But by assumption, this first summand is less than epsilon. So the whole expression is less than 2 epsilon. Okay, and so we see now that for each positive epsilon, we have found a finite rank operator, pt, such that the distance between t and pt, well, the distance is just the supremum of this expression over the unit ball. So after we take the supremum over the unit ball, we conclude that the distance between t and pt is less than or equal to 2 epsilon. And so we see that t can be approximated by finite rank operators. And this completes the proof. Okay. Let's now look at corollary 2 once again. So now we know that for each pair of bounded spaces x and y, we have this inclusion. And we know that if y is a Hilbert space, then this is an equality. So now the initial question is, maybe, well, is it true that these spaces are the same for each pair of bounded spaces? This question was first explicitly asked by Hildebrand in 1931, and later it was given the name of approximation problem. The first man who systematically studied the approximation problem was Grothendieck, and he introduced the following definition. You have a bounded space Y has the approximation property AP for short. If for each bounded space X, the following equality holds. So each compact operator from X to Y can be approximated by finite rank operators. So what we've just proved is that any Hilbert space has the approximation property. So Grothendieck introduced this notion at the beginning of the 1950s. He gave several equivalent characterizations of the approximation property. He has found many relations between the approximation property and some other problems in functional analysis. And he proved that essentially all classical concrete Banach spaces have the approximation property. But even Grothendieck, who was definitely a great man, was unable to solve the approximation problem. So he didn't know if this property holds for each Banach space. So the approximation problem was really hard. And it was hard actually for many reasons. In particular, it was hard because it was closely related to another famous problem of functional analysis, namely the so-called basis problem. So let's give the following definition. Suppose that X is a Banach space. And suppose that we have a sequence En of elements in X. And let's say that the sequence is a Schauder basis. The Schauder basis of X if each element in X can be uniquely written as the following sum. As the sum of the following series. For some numbers Cn. Well, the definition is due to Schauder, and it looks quite natural. It's just a natural generalization of a basis of a vector space. But of course, it's essential here that we have an infinite series. So this doesn't imply that the linear span of these vectors is the whole of X. But on the other hand, it's immediate from the definition that this linear span is dense in X. And this is possible only in the case where X is separable. So let's observe that this definition is meaningful only for separable spaces. If X has a Schauder basis, then it is separable. Well, this is not a serious restriction because most classical and interesting Banach spaces are actually separable. Let's look at some obvious examples. For example, if we take the little P space where P is finite, or the little C0 space, and as usual, we denote by En the following element of X. Then it's easy to see that En is a Schauder basis. So little p has a Schauder basis. Next example is actually a special case of this one. Namely, if X is a separable Hilbert space, then any orthonormal basis of, well, let's note it by H. If H is a separable Hilbert space, then each orthonormal basis of H, we know that it is most countable, is a Schauder basis. This is immediate from the definition of an orthonormal basis. And actually, this is a special case of the previous example, because we know that a separable Hilbert space an infinite dimensional separable Hilbert space is unitarily isomorphic to the little L2 space in such a way that an arbitrary fixed orthonormal basis of H goes to this concrete basis of little L2. The big LP spaces, usually also have Schauder bases. For example, if you take the big LP space over the closed interval of the real line, then it turns out that the trigonometric system is a Schauder basis, provided that P is bigger than 1. This is a rather deep theorem of Marcel Ries, who was, by the way, who was a brother of Friedrich Ries. If P equals 1, then this is not the case. The trigonometric system is not a Schauder basis in L1 by result of Lebesgue. But on the other hand, L1 has another family, the so-called Haar system, which is a Schauder basis of L1. The space of continuous functions on the closed interval of the real line also has a Schauder basis, the so-called Faber-Schauder basis, which consists of, well, piecewise linear functions like this. So almost all classical Banach spaces have Schauder bases. And actually, there was a famous problem due to Banach, which was explicitly stated in 1932, so-called basis problem. Does every separable Banach space have a basis? Does every separable Banach space have basis, a Schauder basis? The answer was given only in 1973. By Per Flo, an American mathematician of Swedish origin. Actually, he constructed a separable Banach space without the approximation property. And it was already known probably this was a result due to Grothendieck, that if a Banach space has a Schauder basis, then it has the approximation property. So Flo actually solved two problems, the basis problem and the approximation problem. So in both cases, we have a counterexample. So Flo's example also shows that the space doesn't have a Schauder basis. Okay. Well, so far we considered compact operators between arbitrary Banach spaces. And from now on, we concentrate on compact self-adjoint operators on the Hilbert space. Well, actually, this will be a brief survey. The proofs of the main results here will be given in our next course in operator theory in spring. First of all, let me explain what self-adjoint means, or more generally, what is an adjoint operator for an operator between Hilbert spaces. Well, let's recall that if H is a Hilbert space, then we have a canonical bijection R between H and H star and the dual space, which is provided by the Rees representation theorem. So this bijection takes each element X to the linear functional, which is the inner product with X. So we know that R is an isometric antilinear bijection. Now suppose that we have two Hilbert spaces, H1 and H2. And suppose that T is a bounded linear operator from H1 to H2. Then we can consider the following picture. First of all, we have the dual operator, which acts between the dual spaces. This is T star. Also have two canonical bijections between H1, H2 and their duals. So let's denote these bijections by R1 and R2. And since they are bijections, we can consider an operator from H2 to H1, let's denote it by T plus, which makes the diagonal commute. And this operator is called the adjoint of T. By definition, the adjoint of T, in Russian, сопряженный оператор, is a map T plus, which acts from H2 to H1. And by definition, this is the composition R1, T star, R1 inverse, T star, R2. So it makes the diagonal commute. Let's observe that the adjoint operator is necessarily a bounded linear operator from H2 to H1. And its norm is exactly the norm of T.
Is it right that if we take, what would it be if we searched for an operator such that if we had an operator between H2 and H1 and we searched for the operator from H2 star to H1 star such that the diagram commute?
Well, the dual operator always acts from H2 star to H1 star. So what was the question? If we start with an operator from H2 to H1.
Yes.
Then the dual operator acts from H1 star to H2 star.
Можно по-русски спрошу?
Конечно, да.
Ну вот, короче, как мы берем Т-звездочкой, по Т-звездочке строим Т-плюсик.
Да-да.
А если мы возьмем исходно, у нас будет оператор из H2 в H1 внизу, а мы будем строить оператор на двойственном. Это же получается... Я просто не очень понимаю, почему, если мы по Т строим Т со звездочкой, это по определению сопряженный. Ну, типа, если у нас есть Т внизу, то Т со звездочкой по определению такой, что вот такая вот диаграмма коммутативна. А если мы Т-звездочку сверху рисуем, то Т с плюсиком внизу не будет то же самое, что Т. Вот, что-то я поэтому запуталась.
Ну, Т со звездочкой просто по-другому определяется. Т со звездочкой определяется вот так. Если f это линейный функционал, да, то Т со звездочкой действует вот так. Вот, и он действует, ну вот если Т из x в y, то Т со звездочкой из y со звездочкой в x со звездочкой. И никак по-другому. Вот у него направление меняется в каком-то смысле. Поэтому тут ситуация такая. Тут мы стартуем с Т. Конечно, Т у нас действует из H1 в H2, видите?
Он в обратную сторону.
Да. Т из H1 в H2, но Т со звездочкой тогда из H2 со звездочкой в H1 со звездочкой. Некуда деваться, его по-другому просто не определишь. Ну а Т с плюсиком тогда опять-таки некуда деваться. Он из H2 в H1. То есть в обратную сторону. Вот.
Спасибо.
Понятно? Угу. Ну, на самом деле, наиболее интересная ситуация, когда у нас одно пространство. И тогда Т с плюсиком действует там же. Т из H в H, Т с плюсом тоже из H в H. Но я про это чуть позже скажу. Okay, so now T plus. What can we say about T plus? I claim that T plus is a boundary linear operator, and the norm of T plus is exactly the norm of T. Well, why is it so? Well, this is true because this is true for T star. We know that T star is a boundary linear operator. And R1 and R2 are antilinear. So it's clear that if we compose a linear operator, T star, with two antilinear operators, then we get a linear operator. And since R1 and R2 are isometric bijections, and T star is, well, the norm of T star is the same as the norm of T, we conclude that the same is true for T plus. So again, the norm of T plus equals the norm of T. It's also possible to characterize the joint operator without using the duals. This is a simple proposition, or rather an exercise for you. T plus is a unique map from H2 to H1, satisfying the following equivalent conditions. Condition 1, the inner product of Tx and Y equals the inner product of X and T plus Y. Or equivalently, we can write the inner product of Y and Tx equals the inner product of T plus of Y and X. Here, X is in H1 and Y is in H2. So this is actually an equivalent definition of T plus, which doesn't involve dual spaces. Let's now look at some properties. Before we continue, let's adopt a standard convention. If we look at this diagram, and if we recall that R1 and R2 are isometric bijections, we see that the properties of T plus are more or less the same as the properties of T star. Well, of course, I cannot claim that T plus and T star are isometrically equivalent because R1 and R2 are antilinear. Nevertheless, R1 and R2 are isometric bijections. So many properties of T star are shared by T plus. So we can write a very long list. Well, T plus is surjective if and only if T plus, if and only if T star is surjective. Well, T plus is topologically injective if and only if T star is topologically injective, and so on. And because of this, we adopt the following standard convention. So from now on, the joint operator T plus will be denoted by T star. Of course, there is a little abuse of notation here, because formally the operators are not the same. But when we work with operators between Hilbert spaces, usually there is no need to work with dual spaces and with dual operators. So when we work with Hilbert spaces, we always denote by T star, not the dual operator, but the joint operator. And usually this doesn't lead to any confusion. Okay, let's now look at some properties of the operation of taking the adjoint. Proposition 2. And this was proposition 1, and this is proposition 2. First of all, the operation of taking the adjoint is an involution in the set theoretic sense. If we apply it twice, then we get the identity map. In other words, T double star equals T. Second, this operation is antilinear. This is slightly different from the respective property of the operation of taking the dual, which is linear. The operation of taking the adjoint operator is antilinear for the same reason, for the reason that the canonical bijections from Ries's theorem are antilinear. If we now take two operators, which can be composed, say, S and T, then their adjoint is T star S star. Here, Sx from Tx from H1 to H2 and Sx from H2 to H3. Property 4 was already mentioned above. The norm of T star equals the norm of T. And finally, property 5 is the so-called C star property. And it is the following identity. The norm of T star T equals the norm of T squared. Well, actually, almost all parts of this proposition are simple exercises. For example, the first part easily follows from proposition 1, which characterizes the joint operator in terms of inner products. Properties 2, 3, and 4 easily follow from the respective properties of the dual operators. Property 5, well, let's prove property 5. It's very important, and on that hand, the proof is quite easy. Well, indeed, on the one hand, if we look at the norm of the product, T star T, well, this is less than or equal to the product of the norms. But we already know that the norm of T star equals the norm of T. So we have the norm of T squared. On the other hand, the norm of T squared is the following supremum. Taken over the unit ball. And if we now use proposition 1, we can rewrite this as follows: T star Tx within a product with X. This is exactly, in fact, we have an equality here. Essentially by the definition of the dual of the joint operator. And by the Cauchy-Bonnikovsky-Schwarz inequality, this is less than or equal to the norm of T star T. So the Cauchy-Bonnikovsky-Schwarz inequality shows that this is this inner product is less than or equal to the norm of T star T multiplied by the supremum of over the unit ball of the norm of X, which is obviously 1. And this completes the proof of the C star property. By the way, this proposition leads to many interesting generalizations. First of all, it leads to the purely algebraic notion of a star algebra. So suppose we have an associative algebra over the complex numbers, which is equipped with an operation, a self-map from the algebra to itself, which satisfies conditions 1, 2, and 3. And in this case, we say that our algebra is a star algebra. If, moreover, it's a Banach algebra, and the involution, so the star operation is called the involution, if it is isometric, that is, condition 4 holds, then we say that it is a Banach star algebra. And if, moreover, property 5 holds, then we say that this is a C-star algebra. The theory of C-star algebras is probably one of the most attractive and rapidly developing algebraic fields of functional analysis, which has many relations to other interesting mathematics, such as geometry, topology, dynamics, quantum physics, quantum groups, and many other fields. I'll probably say some words on C-star algebras in our next course on operator theory in spring. Okay, now it's easy to explain what a self-adjoint operator is. So we'll give the following definition. Suppose now that H is a Hilbert space, and T is a bounded linear operator on H, that is from H to itself. Now we say that T is self-adjoint. В Russian самосопряженный. If T equals T star. Or explicitly, by proposition 1, this means that the inner product of Tx and y equals the inner product of x and Ty for each pair of vectors in our space. Now we have the following fundamental result, which goes back to Hilbert and Schmidt. So usually this result is referred to as the Hilbert-Schmidt theorem. Of course, they formulated this result in slightly different terms. They work with bilinear forms on L2 spaces. And the modern form, in terms of operators, is probably due to Rees. So suppose that H is a Hilbert space, and T is a compact self-adjoint operator on H. Then there exists at most countable orthonormal family EI in H. So it is at most countable. So we may assume that it is either countable, in which case I is just the natural numbers, or it is finite. So I is a finite set from 1 to n. And there is also the degenerate case where I is empty. This case corresponds to the zero operator. Such that the following conditions are satisfied. So roughly, the result states that T is diagonalizable in a sense. So the Hilbert-Schmidt theorem generalizes the well-known result from linear algebra, which states that a self-adjoint operator on a finite dimensional Hilbert space is diagonalizable, in the sense that we can always find an orthonormal basis such that the matrix of our operator is diagonal. with respect to this basis. So this is the finite dimensional result, and the Hilbert-Schmidt theorem is a natural infinite dimensional generalization. So first of all, each EI is an eigenvector, and the respective eigenvalue is real and non-zero. Second, so this formula explains how T acts on the linear span and on the closure of the linear span of this family. As for the orthogonal complement, it is precisely the kernel of T. The kernel of T is nothing but the orthogonal complement of this family. Informally, this means that T can be written in the following way. So if we look at the direct sum decomposition of the closure of the linear span of our orthogonal family and its orthogonal complement, then the matrix, well, kind of matrix of T with respect to this decomposition looks like this. So it is a diagonal operator on the closure of the linear span of our family. It is zero on the orthogonal complement because, well, the orthogonal complement is nothing but the kernel. And here we also have zeros because both the spaces are invariant. Both the kernel and the orthogonal complement are invariant for T. But this is not the end of the story. Part 3. Now, some more information about this family. First of all, this family of numbers, lambda I, of eigenvalues, the set of all these lambda i's is nothing but the set of all non-zero eigenvalues of T. That is the point spectrum minus 0. And moreover, if you take an arbitrary non-zero eigenvalue, lambda of T, we have the following formula. The number of instances of lambda in our sequence is equal to the multiplicity of lambda, that is, to the dimension of the respective eigenspace. And it is finite. And finally, part 5. If our index set is infinite, so it is the set of natural numbers, if we have infinitely many vectors, EI and respect to lambda I, then our sequence lambda I vanishes at infinity. So this result completely describes the structure of compact self-adjoint operators on the Hilbert space. In particular, this result implies the following simple corollary.
Can I ask a question?
Yeah, sure.
Does the sequence of lambda converge to 0? I mean, that it's in C0, or it's in C00?
No, it is in C0. I don't claim that it is eventually 0. It converges to 0, but it is not necessarily. It is not finite in general. It is an element of little c0, but not of c00.
I'm a bit confused. You said that a diagonal operator can't be compact if alpha is not in C00.
No, it's in C0. Let's look once again. Let's look once again at our criterion of.
I see. I understand. Okay.
It was in C0. Look, M alpha is compact if and only if alpha is in C0.
Thank you.
Okay. Okay, so if we assume, moreover, that H is separable, suppose that H is separable, well, for convenience, infinite dimensional Hilbert space, and T is a compact self-adjoint operator on H. Then T is unitarily equivalent. To a diagonal operator. M alpha acting on the little L2 space. M alpha is an element of C0. Here, unitary equivalent means that we can find a unitary isomorphism between H and little L2, a unitary isomorphism, such that the following diagram is commutative. U is a unitary isomorphism. So essentially, this means that each compact self-adjoint operator is diagonal. And this corollary indeed already follows from the Hilbert-Schmidt theorem, because, well, H is separable. This the orthogonal complement, which is the kernel of T, is also separable. So we can find an orthonormal basis here, which is countable. And we take the union of this basis of the kernel with our sequence EI. And this union will be an orthonormal basis of the whole space H. Now it's clear that if we look at the matrix of our operator, so each, well, actually we don't need to involve matrices. We see that each vector of this basis is an eigenvector. So we have found a countable orthonormal basis consisting of eigenvectors for our operator. And if we now use this basis to construct a unitary isomorphism between H and little L2, what we get in little L2 is nothing but the diagonal operator. So this result, the Hilbert-Schmidt theorem and its corollaries, this result is very important. It has numerous applications, not only in functional analysis, but also in some neighboring fields, like, for example, differential equations. For example, the famous Sturm-Liouville problem is to understand the behavior of solutions of the Hilbert-Schmidt or of the Sturm-Liouville problem. It's very convenient to use the Hilbert-Schmidt theorem. Also, there is a famous application in representation theory of compact groups, namely the famous Peter-Weil theorem on representations of compact groups, is proved with the help of the Hilbert-Schmidt theorem. And there are many other interesting applications. In conclusion, I'd like to stress, however, that it's essential here that T is compact. If we drop the assumption that T is compact, then the result fails. And here's a simple counterexample. Let's consider the following operator T on the big L2 space on the interval from 0 to 1, which is just the multiplication by the coordinate. The multiplication by the coordinate. Well, then T is a bounded self-adjoint operator on H. But on the other hand, the point spectrum of T is empty. This is a simple exercise to show that the point spectrum is empty. So this implies that there is no chance to generalize the Hilbert-Schmidt theorem to non-compact self-adjoint operators. we have no eigenvalues. So there is no hope to diagonalize this operator with respect to any orthonormal basis. So this implies that the Hilbert-Schmidt theorem doesn't extend to non-compact operators. Fortunately, there is a suitable modification of the Hilbert-Schmidt theorem, which has a natural analog for arbitrary self-adjoint operators, not necessarily compact. And the respective result of the structure theorem of for arbitrary self-adjoint operators, for arbitrary bounded self-adjoint operators on the Hilbert space, is the so-called spectral theorem. And this is one of the most famous and fundamental results of classical functional analysis. Kind of solution to this quasi-problem, the spectral theorem. So the point is that if we formulate the Hilbert-Schmidt theorem in slightly, not slightly, in essentially different terms, then this new statement can be extended to non-compact operators. And the spectral theorem will be one of the key results, which will be proved in our next course of on operator theory next spring. And that's all for today. And this is the end of our course. Thank you.
Thank you.
Thank you.